Okay, now, okay, thank you. So thank you, Diego. Now we are recording. And so we were talking about capacitance. And so actually capacitance is really simple, I would say, how to represent or understand how capacitance works. So basically, what is going to be happening is if I have two conductive materials or surfaces, remember your chemistry classes. So conductive materials, we're talking about mostly metals or anything that because of their properties facilitate the conduction of electrical energy. So let's think about two metal surfaces. We see that if I have two metal surfaces that are separated by a certain distance, if I apply a voltage source to those two plaques, imagine that the voltage source is kind of like a water pump, and the two plates are kind of like a tank. So the voltage source or the pump is filling in the tank. Something similar occurs here. If I grab two metal plates and I connect them to a voltage source, this is going to turn into a sort of a container of electrical energy. It's going to start filling up with charge. Now, how much charge or how large or small the capacitance is actually going to depend on three factors. That's going to be a question from section 2 of next exam. We haven't said what the answer is, but the question is going to be, what are the factors that influence the value of capacitance in a capacitor? And the three things that influence the capacitance in a capacitor. And they're very simple. First off, let's imagine, just for this example, the sandwich or the Oreo. We've got two time also. We've got two plaques. Let's assume that they're rectangular or square. So there's an area, there's a superficial area of those. Okay. So one of the factors is going to be the superficial area of contact. That's going to be one of the factors.
Superficial what?
Area. Superficial area.
Of contact.
Let me explain what I mean by contact.
The space that is between.
Yeah.
Like the rim
Yes.
of the Oreo.
Yeah, like the rim. So let's say that we've got two this isn't being recorded. Let's assume that we've got two conductive materials, okay? And they're both rectangular. This is a square, okay? Is it clear that both of them have different sizes and both of them have different superficial areas? Which one is larger, the yellow or the white? The white, right? Well, now let's assume that I make a sandwich out of these two. These are drawings that my daughter does. That's why I keep them sure. Let's assume that I make a sandwich out of this. And I can place the yellow square wherever I want. For the purpose of the capacitor, I'm actually only interested in the yellow. That's what I mean with surface of contact. The sandwich is being created between the yellow and the white part that's behind the yellow. The white part that's outside isn't having contact with another metal or conductive surface. Is that clear? That's why we're talking about the surface of contact. We may have two conductive materials, but we're only interested in the superficial area that makes contact. Is that clear with the analogy?
So we write superficial area that makes contact.
Yeah, actually, for the exam, you could just say superficial area. I'm just explaining the superficial area of contact because remember that you're going to have the capacitor challenge for the log exercise. You're going to have to create a capacitor. And so you might say, well, I'm going to do. So this is going to be a large capacitor because I got a large, and then I put this on top. Well, actually, no, it's based on the one that has contact. So for the exam, you could, one of the factors is superficial area.
Okay.
The other factor is the distance between the two conductive surfaces, the distance between. That's going to be the other factor.
Between what?
The distance between the two areas or superficial surfaces, the distance between. Here it's going to be the other way around. A larger sandwich is yummier. Here it's going to be the other way around. The closer they are, the larger the capacity. Are we okay up to this one? We've got two values: the superficial area and the distance between.
The closer they are, they will be larger.
So this is important because of what Estrella is asking. We just mentioned two factors, but we need to understand which factor affects the capacitance being larger or smaller. The larger the superficial area, the larger the capacitance. So if I have remember that we mentioned the sandwich, if I have a sandwich of this size or a sandwich that's the size of the table, the superficial area is larger in the sandwich and the size of the table than the smaller one. The larger the area, the larger the capacitance. It's directly proportional. The distance between the plaques, that's inversely proportional. So the closer the superficial areas are, the larger the capacitance. Okay? The closer they are, the larger the capacitance. So the distance is an element that's inversely proportional. Okay, that's the second factor. Now let's see about your critical thinking skills up to this point, because we have to learn how to extrapolate as engineers. Extrapolate, what does that mean? To infer, correct? That's great, Ricardo. To infer. So we might not know everything, but we can infer things. So I just told you that there are three factors that have to do with the capacitance: the area, the distance. What do you think is the third factor?
The time? I know.
Nope. No time. We're thinking about time, but no time.
The volume. Like the.
No.
The chart? Oh, the question.
Let me say the question. There's three factors. We already know that the area is one factor, and the distance between the plaques is another factor.
The speed, the capacity.
No, the capacitance is what we're looking at.
Charge,
Let's see. Enya?
like the growth of the spot. If it's like.
Actually, that's a good observation. Actually, no. The metal plaques can be very thick or very thin. That's not necessarily going to affect the capacitance, but we're just looking at the superficial area. And the distance between. What could be the third factor? Let me rephrase it so you guys can understand it. Is
How much energy?
well, that's no, the result is a charge, how much it can charge. Let me give you a tip.
I mean.
If we're looking at this at the sandwich, is a sandwich that just has let me finish. Is the sandwich that just has ham and cheese tastier than the sandwich that has ham, cheese, lettuce, tomato, maybe some dressing, maybe some bacon? The component, whatever is in the middle.
Oh.
So remember that we're creating a sandwich in a capacitor. So one factor is going to be the area, the other factor is the distance, and the third factor is whatever we're putting inside the sandwich. You mentioned permittivity.
Yes.
That has to do with that. By default, The material that's here in the middle has a name. It's called a dielectric. That's the material that goes in the middle. It's called a dielectric.
So we put depends on the
You can, for the, if we're talking about the example, any of these answers could be correct. You could say the third factor is the dielectric. The third factor is the permittivity between the plaques are related to that, or the material, or you could just say the material that's between the plaques. Okay. Now, whatever is here inside, that material is called a dielectric. Now, this is important. We're talking about the plaques that they have to be conductive. So we've got two aluminum plaques, okay? And I'm gonna put, so I've got two aluminum plaques, and what I'm gonna put in the middle is I'm gonna put a copper.
What are plaques?
Oh, plaque, I'm sorry, plaques, I'm gonna say it's plaques, plaques. Just something, something plain that we're putting together. So this is a plaque. PLAQE. And if I put copper in the middle, that's not going to create a capacitor. If I put steel, if I put gold, if I put silver in the middle, that's not going to create a capacitor. The capacitor sandwich has to be conductive material, something that's not conductive, and then conductive material. And that material in the middle, it's called a dielectric. It's an insulating material. It's something that by default is not going to conduct, but it's going to help me store things. And so by default, the property of materials that has to do with the allowance of conducting electrical energy, that's what's called permittivity. We've already mentioned that. That's an electrical constant. Permittivity, and it's represented with this E. For like permittivity, like
Is it, no, is it gross, is it, we didn't make it.
permittivity.
With
I'm
the.
not sure if it's with a double T, by the way. I don't know if that's a typo.
It's just a question because it's not, I don't know, it looks weird, but I don't know if it's just my.
Actually, I think it is with a double T. Yeah, permittivity with a double T. It does look weird, but it is with a double T. Permittivity. I'm gonna say it this way, and it's being recorded. I never grade or deduct points for spelling errors. I sometimes make fun of them when they're really, really funny. And I make notes, but I'm never gonna deduct points because something that's really, it's not correct. So it's permittivity. Okay, somebody drew something.
Yeah, I have a question.
Yeah, go ahead.
Those
No, that's perfect. Let's go ahead.
So like for the superficial area,
Mhm.
so if we have the smaller plate and the, for example, that red plate. The superficial area would be the smaller plate.
Correct. Yes, that's exactly, it's a very important. The superficial area is only the area where there would be a direct contact for the sandwich. Correct.
So like so the capacitance would be the same of the small sandwich and of the irregular sandwich.
Mhm. Because you're just focusing on the surface that the contact surface.
Okay.
And so going back to the dielectric, which is the material that goes in the middle, by default, the reference for permittivity is called permittivity 0, which is permittivity of vacuum. Remember that in physics, the reference is vacuum. Vacuum is space where there's nothing there. There's no particles. There's not. So the reference is permittivity 0, which is the permittivity of space. Okay. And so different materials have different permittivity. So foam has a permittivity, wood has a permittivity, wax has a permittivity. Different materials that aren't conductive have different permittivity. depending on the material, is going to be the value of the capacity. Okay, so those are going to be the three factors: the surface area, the distance between the plaques, and the material that we put in the metal. Okay. Questions up to this point?
Another question.
Yes,
You
yes.
mentioned that you can't put gold in gold because is gold conductive? I thought it wasn't.
No, any sort of, actually, gold is very conductive. If we could have wires made of gold, that would be great, but it's really expensive.
It's one
So-
of the best conductors.
It has a very good conductivity, gold, silver, etc. But again, you're not gonna make, or you could make gold wires, but they're gonna be really expensive, and they're actually gonna be really expensive and really heavy. So it's not a practical material to use, but it is very conductive. It is very
There are
conductive.
some things that have gold.
Because I remember reading an
Wire.
article.
It's a pursuit. Because I think I have heard it, but I'm not sure.
It's probably gold, some sort of gold lining for a very specific application and in a very small proportion.
Because I remember reading about the rover Perseverance, the one that's on Mars and launched about a year ago. I think in February. She has like a golden box that converts the CO2 in Mars into oxygen.
Mhm.
And I read that they chose gold because it doesn't react with the metal.
That's true, but it's still
But
conductive.
it's conductive.
It's conductive. It is a conductive material. Any sort of metal is a conductive material. There's different levels of conductivity. That's actually something very interesting that we're going to talk about next semester, not this semester, in industrial electronics. There are things that are called conductors, usually metal, and then there are things that are called insulators, which is a total opposite. An insulator is something that does not conduct electricity. A lot of dielectric materials are insulated. They don't conduct electricity, but they can be used as part of the sandwich to be able to store electrical energy. And then there are these things in the middle that are called semiconductors. And if you've heard the term semiconductor is associated with computers. The semiconductor industry, it has to do with computers and electronics. And semiconductors are these things that are kind of in the middle that sometimes can behave as conductors and sometimes they behave as insulators. And we can actually control them. We're going to be talking about that next semester. But so in the capacitor, we're going to have those three factors. And actually how they're related or how we can mathematically represent it is actually very, it's actually very simple. Oops, I didn't want to open the video. So, assuming that we would have a specific example, and we wanted to calculate the capacitance of this, how would we do that? Well, actually, the mathematical expression for capacitance is very simple, according to what we just mentioned. The capacitance is going to be directly proportional to the area, and it's going to be inversely proportional to the distance, and it's going to be related with. So the capacitance expression as a mathematical expression, capacitance is going to be equal to the permittivity of the material. It's directly proportional to the permittivity of the material. It's also going to be directly proportional to the surface area. Capacitance, yeah, that's C. It's going to be directly proportional to the permittivity and the surface area, and it's going to be inversely proportional to the distance between the plaques. The capacitance formula is a very simple formula. It's a very simple expression. And just remembering that this E here is permittivity with a double T, and that this E here has to do with the dielectric. Is it a constant? Yes. it's going to be a constant depending on the material. So for example, for this example specifically, it says a capacitor is constructed from two conductive metal plates that have a certain dimension. They're spaced 6 millimeters apart and use dry air as its only dielectric material. By the way, dry air is the closest thing we could say that's approximate to vacuum. Okay. So for this case, the permittivity that we would use is a constant, which is called permittivity 0, which is the one for vacuum.
For what?
For vacuum. Don't forget if vacuum is with 2 C's or not. No, it's one. It's 1 C and 2. I played Wordle last. Were you guys playing Wordle?
I did the workshop.
I started playing it. It's fun.
I did it.
But I got annoyed with the ads, and I don't know if I want to buy it because I'm gonna be obsessed with it. There's a one that's without ads.
You're supposed to go to newstimes.com and there's one every day.
Oh, okay, it's not the app then.
It's every 24 hours, you put a new word and we create the.
Oh, and that's in New York
New
Times?
York Times.
Oh, okay, I'm gonna check that out. I find those games fun.
It's
And that's a good way to practice English, by the way. You can make another word.
Baby Wordle, and everyone does it. Well, you have to guess
Casi como
instead
Wordle,
of-
pero pequeño. It's because we are divided with the same professor.
For the workshop.
And he plays with us Wordle
Okay.
and with them.
Usually
He makes TikTok.
TikToks, yes.
Who is
So
it?
you wanna see?
No,
Jose Ramon. You wanna see?
Jose Ramon, what? What's his last name?
I have no idea.
Just Jose Ramon. It's like Bono. It's like Bono or the Edge. It's like one.
He's the one that put it together. Although.
Sí.
You did
You wanna
TikToks in the
see it?
class? Sure.
El mío es el mejor,
At the end. At the end, not in that part.
Oh, no, that's the.
Ay, y
Wow.
no volume, wait.
You're gonna get in trouble.
Look video.
You're gonna get in trouble.
Oh, you got some skills there. Wow, you like that?
Ah, you didn't tell the professor, right?
I saw.
It's the last one.
I told my wife repeatedly that we should get on TikTok because of what the stuff my daughter does. But and we would be on TikTok
Yes, you
24/7.
We could repost your TikTok.
I could, yeah. I don't know if any of you have
Like
seen
John
the.
Green and the, John Green.
The name
It's
rings a
an
bell.
author.
Uh-huh.
He has a brother, Andy Green, and he makes TikToks about like scientific stuff.
Stuff and all that.
People ask.
It would take up too much of my time. Have any of you seen the series? Have any of you seen the series Peacemaker?
No.
Okay, just you don't have to watch the series or anything, but just Google Peacemaker intro. There is a dance sequence that John Cena does with the whole cast. And we're actually in my house with my wife and my daughter, we're practicing to try to learn the dance sequence. So you can just Google that. So if I get on TikTok, you're probably gonna be seeing that there. So coming back to this, well, it's very direct. If we want to find the capacitance of this capacitor, well, we just need those values there. So the area in this case, or the superficial contact area, is, since we're talking about two metal plates that are rectangular, they're 30 centimeters by 50 centimeters, so the area is going to be 0.3 meters multiplied by 0.5 meters. This would be, that value, this would be what, point 15? No. Point 15.
Grace.
Okay, the distance, it says that it's 6 millimeters apart. Obviously, that the distance is going to be a very small distance. This is going to be, the distance is, okay, remember about the noise level, settle down. It's going to be 6 millimeters. They're 6 millimeters apart. So the distance would be 0.0.
0.006.
0.006. 0.0, is it 10? Let me just check here.
With 2 zeros, and we didn't have to.
Yeah. Times is 10 to the minus 3, so it would be. Six times 10 to the minus 3 meters. And the permittivity in this case of vacuum is a constant. That's going to be a constant. You can Google that constant. It's something that it's similar to the K that we've been using up to this point. This is 8.85 times 10. Just verify that value. Let's get confused with the to the minus 12. For vacuum. Depending on if we're going to see some tables. We're going to be seeing some tables later on of different dielectric materials that have different epsilons. So you can check what is the permittivity of wood, what is the permittivity of plastic, and you're going to find different constants for each of them.
And it doesn't have a unit.
The units would be, we can find the units here, they would be meters. I don't want to write that down incorrectly. We've got it on this on the next slide. It doesn't have the units here. A moment. The units can be represented differently. Farad meters. We haven't mentioned something here. Excuse me? The units are farads by meter. We haven't mentioned something up to this point. We haven't mentioned something up to this point. The units of capacitance are given in farads. The units of capacitance are, or the capacitance unit is going to be the farad. And it's represented as an F. Farad is because of Michael Faraday. And Michael Faraday did a bunch of things. We're going to be mentioning him in the magnetism unit as well. Faraday cages, there's a bunch of things that have to do with Faraday's law, and so this unit is named after him.
So Edward Farad, what?
Farad. That's up there. Farad. Farad. I hope any of you guys or some of you guys will get to do something so cool that they name a unit after you. That would be so cool.
Castellan.
Yeah. I would love something to be called the Sosa.
Sabemos patadas, era Cobra Kai. No,
Uh,
este lo intentó como 10 veces, ese fue el bueno.
And so let's calculate the capacitance is gonna be, I'm gonna do it here on the bottom, the capacitance C is gonna be the combination of these, it's, I'm not gonna write the units, it's gonna be 8.85, yes.
We're always going to use that value for permittivity.
Oh, that's a good question, that value of permittivity, notice that I put the 0 on the bottom, that's the permittivity of vacuum. Okay, for this problem, it says it's using dry air. Dry air is the closest thing to vacuum, so it's 8.85. That's epsilon 0. If, for example, I would say, you know what, the material in the middle is wood, just to give an example. Then you would need the value of the permittivity of wood. These are constants. So either I'm going to give it to you, or the problem is going to give you the value, or you might have to search for the value.
Ah, okay, that's what I want.
Yeah. So usually in most of the situations that we're looking at, the values are going to be given to you. For example, for your challenge, for your capacitor challenge, you're going to have to, you're not going to be doing a capacitor where whatever's in the middle is air, because it's going to be very near to impossible to do that. Okay, if your capacitor, there's going to be air in the middle, it's going to be very difficult for things not to touch. You need something in the middle. So you're going to have to research. You're going to Google, what are good dielectric materials? Paper is actually a dielectric. Paper is a dielectric. You could put a piece of paper in the middle of the glass. That would create a capacitor. Have you guys, so I don't know how many of you guys cook, but yeah, the wax paper that's used for cooking and used for cooking sheets, is it wax or something like that?
Yes.
It's called a papel encerado or something like that. No, you don't put that in the oven, right? But what, if you can't put it, what is the wax paper used for then? For what? And then it doesn't stick. Yeah, that's what it's for. So wax paper can also be a good dielectric. So when you find these alternatives, then you're going to go on Google and say, well, what is the dielectric of wax paper? Well, the dielectric of wax paper is going to be whatever. And sometimes we haven't gotten to that, to mention that, but it's in the slides further on. The dielectric of materials can be represented, the dielectric value of materials can be represented usually two ways. As a value, so there's going to be an epsilon for wax paper, and it's going to be a value, okay? Or they're going to give you a K. And the K means that it's just to give an example, the dielectric value of wax paper is K equals 2. That means that it's 2 times the value of vacuum. Always the value of vacuum is going to be a reference.
2 times 8.85.
And so if you look at dielectric tables of materials, and by the way, that's in the, we're going to see that's further on, and I'm going to show you some examples. They can give you a K. The dielectric material of wax, the K is 10. The dielectric constant of paper is such, and it's a multiplier or a reference of epsilon 0. And just to finish this up then, this is multiplied by 0.15 divided by 6 times 10 to the minus 3. And so what value did you get of the capacitance? By the way, it should be a small value.
2.215.
Oh, that was even in harmony. You guys could have made a band or something. You guys, it almost sounded like singing. You said the 2.2 in different tones, and it's not. I was hearing Taylor Swift in the background. 2.212
times 10 to the minus 10.
and the units are farads. This is important. Farads are gonna be the units. Remember that we're gonna be working with very small units. In the previous learning module, we talked about coulomb. 1 coulomb is huge. A unit of 1 coulomb is something very big. A capacitor of 1 farad is a huge capacitor. That's why usually farads are going to be in small values. Okay. When we find a capacitor, we're usually going to be talking, we're going to be needing a 20 microfarad capacitor. We're going to be needing a 10 picofarad capacitor. They're usually very small values. So it's not odd to find this times 10 to the minus 10. Okay. Did we get that value or something close?
Yes, I was getting something different, but.
So farads are going to be very small units, very small units. It's not uncommon for that. Okay, questions with this one?
No.
Can I clear the screen?
Yes.
So that's 2.2. Well,
What are you doing, Professor?
Times 10 to the minus 10. What am I going to eat today? We have a routine at home. My wife is working, and thank God for that because she's working. I can buy nice things. And she hates it when I make those. She really doesn't like me making those comments. I always joke with her that I want her to become a very important manager so I can retire and be a stay-at-home dad and to cook and all that. And she gets really angry with me. We have this routine since my wife is working. So I go pick up my daughter and at school, and then we go to my parents' house and we eat there with my mother. And my mother usually, whatever my mother cooks is gonna be good. And there's gonna be homemade tortillas, always. Always.
I know how to do homemade tortillas.
You know, that's an important skill. I'm gonna say it this way, whoever is the young woman that is fortunate enough to be dating you, and if you know how to make homemade tortillas, you need to tell her because she needs to put it.
My grandma teach me.
Oh, it's a grandmother recipe. Oh, that is a skill. Making homemade tortillas, that's a skill. It's not everybody can do it. There was this thing usually the routine at home is that since my wife is working, we go eat with my parents. So that's normal. When my wife was pregnant with our daughter, because my wife cooks very, very good also as well. She's a great cook. When my wife was pregnant with our daughter and she was at home, I went to eat at home. I didn't go with my parents. And my wife cooked, and she's a great cook. And I ate really well. But my wife is more like I would say a healthy when she cooks. So she cooks healthy, but very, very good. And I started getting thinner. And everybody's like, why are you getting thinner? And the math was really simple. In my house with my mother, it's old school. So if she does, I don't know, carne asada, it's gonna be a carne asada with chorizo, with beans, with a stack of tortillas, homemade tortillas. So when I went to eat with my parents, I mean, I got really filled. I mean, it's yeah, I can eat about 10 or 15 tortillas in one sitting because they're homemade and they're just out of the. And that's why I got thin, because my wife cooks great, but she didn't do these mother or grandmother proportions that are huge. And with my daughter and I, since we've been going to eat with my mother, it's like we finish eating and we're like, oh, we need to take a nap. And both of us just take a nap. So I don't know what we're gonna eat, but whatever we're gonna eat, it's gonna be good. What are you gonna eat? No, you need to eat something.
She never eats because my mom doesn't cook. I need to cook for myself every time.
You do? And what do you like to cook?
I just know how to cook for you in pasta. Pollo con pasta.
Pasta? I mean, I could eat chicken and pasta. That's you could do a chicken sandwich. If you got pasta, you could do a chicken salad.
I will.
I hope you guys have a good lunch. Yeah, lunch is important. Okay, we're gonna